Welcome back. Clustering is an important technique to process unlabeled data. Today we will discuss how to cluster a set of observations that are unlabeled using what's called the k-means algorithm. So we'll start with this example. Now here, let's suppose that we have an unlabeled set of data or set of handwritten image digits that are given here. Each one is an image, which is a two-dimensional vector or two-dimensional matrix. So then we can consider this two-dimensional matrix as, by flattening it, we can consider that as a one-dimensional vector. So now you might imagine that if you take this vector and a vector that represents another three, that might be quite similar in terms of where the pixels appear for that. So the idea would be to see if we can find the close vectors or group vectors into similar vectors based on some criteria that will allow us to cluster these images. So in this case, we're going to be using something called k-means clustering. The k-means clustering is an important and easy to understand algorithm that is not so much efficient, but it's a very good algorithm. So in k-means algorithm, we got some unlabeled data, and then what we like to do is to find two means, mu1 and mu2, that represents the cluster. In other words, we will say those are the points that represent all these clusters here. So let's start with an example. Let's suppose that we have 5 points, these 5 points in R2. We're going to pick 2 points randomly. Let's assume that randomly we pick 1, 1 and 0, 1 from these points. Then what we're going to do is we're going to compute the Manhattan distance to these random centers that we picked from each of these points. We define the Manhattan distance as the difference between the x-coordinates and the difference between the y-coordinates, absolute value, which is sort of like going from one point to another point. That's the Manhattan distance. So here, let's talk about one example. See, if you take the distance between 0 minus 1 is 1, 1 minus 1 is 0, so the total is 1. So if you take another random point here, it's 2 minus 1 is 1, 3 minus 1 is 2, so you get the 3 here. So now the idea is to see which points, which one of these 5 points belong to the clusters represented by these centers. So what we're going to do is we're going to look at the minimum in a column. So the minimum one is the closest. So therefore we say that this point belongs to that cluster. And then the same thing here. Minimum is this one, so we say this point belongs to that cluster. This point belongs to that cluster because that's the minimum of 1 and 2. Same thing here. So therefore we came up with 2 clusters where one cluster has only 1 point, the other cluster has 4 points. And the total loss is that when we estimate a cluster by a point, how much loss that we have. Here we have a 0 loss, here we have 0 loss, here we have 1, 3, and 3. So we have a total of 7 loss here. Now to the second iteration. Now that we found 2 clusters, what we're going to do is we're going to find the mean, the average of the center of this cluster here. To find the center of the cluster, you add the x-coordinates, divide by 4, add the y-coordinates, divide by 4. So with that, you're going to get this. And since this cluster has only 1 point, it remains the same. Now we do the same thing. We find the Manhattan distance between this point and that cluster. That come out to be 1.9, 0.9, 1.9, and so on. So you can check to see if these numbers are correct. Now based on these numbers, we're going to come up with another clusters. Now we find that this point belongs to that cluster. Therefore now we have a cluster that contains 2 points here, which is 0, 1, and 1, 1 is in that cluster. But still these 3 points are in the second cluster. So again, we look at the loss by looking at the minimum loss we have for each cluster, 2.1, 2.1, came out to be 7. That might be slightly less than 7 because we have rounded it. All right, so now we made some improvement. Here we went from 1 point in that cluster to 2 points. You can also notice that these 2 points are closer, so they are supposed to be in the same cluster. Perhaps we will be able to catch this point as well in the next iteration. So next, go to the next iteration. In the next iteration, what we're going to do is we're going to find the cluster centers. So we're going to find the cluster centers here by taking this cluster. That cluster center is going to be 1 over 2 plus 1, right? So it's 0.5 and 1. So we find that cluster center here, 0.5 and 1. And then here we find these 3 points. We add the x coordinates, we add the y coordinates, we divide by 3 to get the next cluster center, which is 2 and 1.6. And we do the same thing by computing the Manhattan distance between each of the points and the cluster centers. We come up with this number here. Now, if we look at the minimum, then we see that now we are really finding that these 3 points actually belong to the same cluster, which makes sense, right? And then these 2 points belong to another cluster because this is another cluster here. So now we look at the total loss is now 5.3. So this means we went down in the loss here. Now you can continue the 4th iteration, although you might not improve this loss, but you can try it. In the 4th iteration, what you need to do is to get the center by taking the average of these points, which goes in here, and take the average of these points, which goes in here. And then compute all the things like we did before and see what the total loss is. Now, if the total loss doesn't go down or increases, then it's time to stop. All right, so when do we stop? As we iterate, how do we decide when to stop? We assume that the loss will decrease as we iterate, as we do more and more iterations. If you're looking at this, basic idea would be that we plot the loss versus the number of iterations. And at some point you might decide that it's not worth going any further because that loss is good enough. I can accept this loss and then stop it there. So we can stop iterating at that point. So we pick the cluster center at that point and you're done. Now here's the k-means algorithm. We start with m data points, each with, say, dimension n. We randomly pick k clusters. That requires k work. Then we find the distance from each of the clusters to each of the points. And that will require k times m work. Then we choose the minimum such thing so that it belongs to a specific cluster, the jth cluster, for example. Then we recompute the mean by taking all the points that belongs to a specific cluster, j, for example. And we do that for k things. So this is what the k-means algorithm does. And you can implement k-means using x as the matrix of all the observations. So here x is a matrix, and k is the number of clusters you choose, and this one says you can iterate 10 times. I won't go into the details here, but you can see that the idea of this is to minimize this quantity here. So we're trying to look at that difference between the x minus mu. So mu is sort of the, this is the observed, that's the observed, and this is the estimated. Because in our case, we estimate a point by its center. So if you take this one, you can kind of see how that relates to this expression there. The rest is hopefully you will be able to understand or implement on your own. All right, so we'll look at the implementation next. So as an implementation of k-means, let's go with some sample code here. So this is the function you saw in the lecture, which is defining how to find the k-means. This is the k-means matrix x, k, and the number of iterations. Now in this case, what we're going to do is we're going to use a real data set which has 5,000 rows of housing data, but we're just going to focus on two features, the house age and the number of rooms. So here's the data file with 5,000 things, but we only consider two rows here. One of the important things about any machine learning algorithm is you must normalize the data. So normalization of the data means that you do the, in this case, min-max scale. In other words, the minimum point here mapped to 0 and the max point mapped to 1. So all the numbers are going to be between 0 and 1. So even if there's a scaling issue here, that doesn't matter because now we are in the same scale. So we still have those things. So before we can apply the k-means, we want to convert our normalized data frame into a NumPy array. And the NumPy array shape is now 4,999 things in 2 columns. And we apply the k-means algorithm here, 2 iterations, and then we can find the centers that it found and the loss. So it shows the centers and the loss. These are center points that represent each of these observations here. So remember, there are 10 points. Now we can see how this works by delaying a little bit and going through the process. So you can see the loss seems to decrease as we go through the k-means. Each iteration, we expect the loss to decrease, and the loss is decreasing. So at some point, you can decide to, this is going to do 30 iterations, but you can decide to do less iterations and stop it, or if the error seems to go up, then you can stop. So here we are going to 30 iterations. I think that's done. So that's the best thing we can get. And now we can look at the centers with that 30 iterations. What are the cluster centers? So we have their data points and the loss that we recorded here. Now, if you plot this, you can get an idea. So when you plot it, you can see the 10 cluster centers here and all the 5,000 housing data as points here, age and the number of rooms. Now, we can do interactive exploration of the k-means algorithm. So finding a good k is an important part of this. So here we can see we're going through k-means with, we're doing 6-7 clusters here. So we are using some colors here, obviously, and going through the k-means algorithm, and hopefully we are reducing it. So here, another way to look at the k-means, you can see how the initial centers are. So this is like an interactive exploration. So we choose centers randomly in various places, but notice that the centers begin to move to their centers. So slowly moving, and eventually they'll settle down in the middle, which middle means that it minimizes the total error. Now, finding a good k is always a problem or a challenge. What we like to do is to plot the number of clusters. So we try number of clusters versus the average loss. And at some point, if you say that 15 is good enough, so that 15 is what we go with. So choosing the number of clusters is, like I said, the challenging question. Sometimes depends on the domain knowledge. If you know something about how many groups what we're supposed to have, then it's fine. You can choose it. If you don't have an idea, maybe this will give you an idea about when you can stop. So that's all for now.